Hi there, welcome to my channel Mando to Fundo. In this video, I am going to discuss about the solution to inverting the binary tree. Let's look at the problem description. We are given a root of a binary tree and we have to invert that binary tree and return that root back to the caller. So let's look at the example 1. So here we are given a tree which has node 4 as the root and it has two children 2 and 7, and which two in turn have children 1 and 3, and 7 has 6 and 9. So after inverting, so the 7's old left child becomes the right child, old right child becomes the left child. Same thing, 2's old left child becomes a right child, 2's old right child become a left child. First this is done, and then one level we go back up, and then the 4's right child becomes a left child and 4's left child become the right child, and we eventually return the pointer to the root node. The same thing here. So the left child of 2 is become the right child and the right child of 2 becomes the left child. So the constraints are the number of nodes in the tree is in the range 0 to 100, and the value of each node is ranging from -100 to 100. So we are given a tree 2 1 3. 2 is the root and 1 is the left child and 3 is the right child. After inverting, the 3 will be left child and 1 will be the right child. So how we can do that? So basically we can perform the post order traversal and perform the inverting operation on the children, and then the inverted subtrees will be attached to the parents recursively as we reach the root node. So whenever a parent node is visited, first we have to invert the left subtree and then invert the right subtree. Then invert the left subtree will be attached to the right as a right child of the root. The inverted right subtree will be attached as a left child of the root. So we will do it as we go up. We build this inverted tree from bottom up. Let's look at the flow chart. Input for this procedure is root pointer to the root node. First we check whether the root node is null. If so, we return the root node as it is. Otherwise, we make a recursive call to invert the left subtree of the root and then assign the return value to the variable left. Then make a recursive call to invert the right subtree and assign that return value to a variable right. Then assign the variable left as the right child of the current root. Same way, assign the right variable as a left child of the current root node. Then we return the root. Finally, we get the inverted tree pointed by this root node. Let's move on to coding. First, I check whether the root node is null. If it is null, I return it immediately. Otherwise, I make a recursive call to invert the left subtree and assign that inverted left subtree root to the inverted left variable. Same way, I do invert the right subtree as well and then assign that root of the right subtree to the inverted right variable. Then I switch the right and left child of the root node. So I make the inverted right as the left child of the root and inverted left as the right child of the root node. Then I return the root. Next I am going to run the test cases. All the tests passed. Next I'm going to submit this program. Cool, this program is accepted. Next I'm going to do the code walkthrough with sample input. Let's do the code walkthrough for this input. The input tree has 4 nodes, 1, 2, 3, 4. So 1 has 2 child, 2 has 1 left child. Okay. So initially the root is passed to the invert tree function. We check whether it is null. It is not. So we go ahead and try to make a recursive call invert tree for the left subtree. So basically we are trying to invert the left subtree first. So this will trigger the creation of frame 1. So we are at processing this node. So inside we are checking the root is null, not. Then we make a recursive call to process its left child. So it creates the frame 2. So the frame 2. Okay. So the frame 2 process the node 4. It does not have any left or right child, and this node will eventually return back to the caller, which is the frame 1 that process the node 2. Okay. So basically because this node do not have any left or right child, the tree structure remains same. Okay. So after this is done, when it goes back, the node, the stack frame which process the node 2 here, the control comes here, and we make another call to process the right child. Because the 2 do not have any right child, we simply immediately we hit this condition and immediately we return back, and the right will have a nil, the left will have an node 4. So next step what we are doing, we are inverting the childrens of node 2. So right now the right is pointing to nil, we are assigning that to left pointer, so we are making this as a left child, so this becomes nil, and we are assigning the current inverted left to the right pointer, so the node 4 becomes right child of node 2. So once this is done, the control goes back to frame 0, which in turn makes a call to do invert this node. So that is what we are seeing in frame 1, processing the right child of root. Okay, because this do not have any children, immediately we return back. When the control comes back to frame 0, the left contains the inverted left subtree, and the right variable contains the inverted right subtree. So the next thing what we do, we assign the right subtree, the inverted right subtree, to the left pointer to make it as a left child, and then we assign the left variable to the right pointer to make that as a right child of the root node. So once we swap that, finally we get 1, 3, 2, and then nil left child, nil left child, right child, and then nil left child, and then 4. So that is what the expected output is. Next, I am going to do the time and space complexity analysis for this solution. Let's do the time complexity analysis for this input. So the input will be 1. So the given input is a tree with 4 nodes, 1, 2, 3, and 4. So the time complexity is order of n. In order to invert the entire tree, we need to visit all the nodes. So it is order of n. So the space complexity is varying depending on the nature of the input. If the input tree is a complete binary tree, then the number of maximum stack frames created is log n. That is the height of the tree. So that's why for the complete binary tree, it is order of log n. But for the case of skewed tree, we need to make a recursive call with depth n. So the space complexity for that case is order of n. So let's consider this as a worst case thingy. So the space complexity of this solution is order of n. Thanks for watching this video. Have a great day.